Okay. To solve the second part, right? We know that we have to calculate this conditional probability, right? And we will just use again the definition, right? Just the definition. We don't need anything else. Just we only have to remember the definition of conditional probability, right? Actually, okay, let me write it first, right? So that's for the numerator. For the denominator, right? We have what? The conditional, no, the probability, unconditional probability of the second part, like this, right? So we can just go a long way to calculate this, or you think a little bit carefully to understand what exactly this means, right? So this is the same as saying what? I want the probability that George hits the target and together the target has been hit at least once. Forget about the probability, before you calculate the probability, what can you say about this event? Is there any simpler way to express this? George hits the target and target has been hit at least once. So I guess what you are saying that the G intersection H1 union G intersection H2, was it what I understood or something else? What you are saying?
Yes.
I am just trying to find even something simpler. If George hit the target, then what do you know about how many times the target must have been hit? Yeah, so this automatically happens. Right? G is in fact a subset of this set. Right? If G happens, this set will have, or this event must have happened automatically. Right? So G is if, right? Do we agree on that? Right? G is a subset of the union of H1 and H2. Do you agree with that? If G, namely George, hits target once, you right away immediately know that the target must have been hit at least once. Right? So this event will have happened if G has happened anyway, right? If G is a subset of this set, the intersection of a subset with a superset is going to be what? Small set, or set small subset is itself, right? So this is actually the same as G. Right? So we don't have to do that. So you can do that. Actually, I didn't think while I was doing the calculus. I just did just what you suggested, right? I distributed this calculator and then realized that actually I didn't need to do that. Not that big deal, but sometimes it is good just to think when you're trying to calculate. You can just find short cuts to your calculus. So, okay, this is the same as even G, therefore the probabilities must be the same, so I had that. Well, what can I say about this? First of all, these two events cannot happen at the same time. The target is going to be exactly once or exactly twice, right? So they are disjoint, therefore the probability of the union is the same as the sum of the probabilities of these marginal units. We cannot do any better than that, so we have to just deal with these two things separately. What is this? Wow, okay, have we calculated this before? Probably. Do we? Have we calculated that? Where is that? Ah, it is this. Okay, here in denominator. So we just go like this. Right. Okay, this is 0.54. Now we have to deal with this. Let me just use this part for that purpose. Right? Well, before we calculate, well, worry about the probability, you should have actually written this, but let's just do both steps at the same time. H2 by definition is the event the target was hit exactly, well, twice. So this is what? B intersection G, right? And since B and G are independent, right? So this is just a product. I don't know why I am doing this. Okay. There's nothing wrong with it, but okay. Product of B times product of G. Right? and we know the numbers, right? It is 0.7 times 0.4, right? And this is not 0.28, right? That's my favorite. So we can put it here, right? And we also know what this is. This is 0.4, right? And we can just write what? This is going to be 4 over maybe 40. Right? When I sum these two things up, we have 7, 8, 82. Am I right? Yes, that's correct. And we can just cancel maybe only once. It is something like this. It's slightly less than 1/2, right? Slightly less than 1/2. Okay. Right? Right? Okay, this part was kind of interesting. This teaches us that we have to pay attention a little bit more than what the question says. Right, okay, so much example about conditional probabilities. Probably enough. Do we have any questions about this? No? You're fine. Let us just go ahead and also remind ourselves what a random variable was. Soon we will define a stochastic process as the collection of random variables indexed in an appropriate way. So before we do that, it would be better to introduce what a random variable is, right? And a random variable is just a mapping from sample space to real life. So sometimes we give a name, okay, a random variable, right? Right? X. So usually we use capital letters to denote random variables, and lowercase letters to denote their realizations. Okay, a random variable X, right, is a real valued mapping or function, right? So let me repeat it again and emphasize what the statement is actually telling us, right? Okay. From the sample space, right, which is omega, to the real numbers, which is right. So the name random variable is a little misleading. It is not a variable, actually. It is not just a number that you fix and that's all. For every different realization, X will may take a different value, right? So what X does is it takes each and every one of the realizations or members of this set and assign to them a number, a real number enough, right? And it would have been more appropriate just to call it as a random function, but somehow, I don't know who started this, people call it once as a random variable, it stays like that. You should never forget that it is a mapping, because that's going to be important when we define the expectations and other functions, variance, or moments of this thing, to remember that actually it changes over the sample space. Right? An example, if you just look at the first random experiment that we defined, namely if you, for example, okay, you roll 2 dice, right? Right? In that case, right? So see, in the definition of random variable, there is no mention about the probability, right? We are not talking about probabilities. This is just what happens, okay, a number associated with each outcome before you even start worrying about the probabilities or likelihoods of different events, right? So omega, in this case, okay, we roll a dice, right? So it has how many faces? 6, right? You look at the numbers, right? Okay, I should just, okay, roll 2 dice. Okay. How can you just summarize all possible outcomes that comes out of this experiment? We can just use 2 tuples, right? you may have seen one on one face and one on the other face, or it just goes like this: 1 to 2, 1 to 3, 1, 4. I know it is boring, but I need to do this at least once. Okay, like this, and then perhaps, well, if you somehow just regulate, right, then you know what the first die is, right? So 2 to 1, 2 to 2, 2 to 3, 2 to 4. I need one more of this, right? And it goes like this, then 6, 1, 6, 2, right? Okay. 6, 3, okay. It goes like this, 6 and 6, right? So this is now the domain for many functions that you can define on the set, right? And each one of them are going to be a random variable for us, right? And some of them are going to be interesting, some others are not. For example, we can define x, right? Right? X is the sum, let's say, sum of the numbers on the faces of those two dice, right? Right? So this is, even as I write, it's probably not appropriate. So what you know that is actually this is a number associated with each omega coming from this set or this set, right? So some of the numbers on the faces of two dice, right, is actually associated, but it's going to change, of course, right, with the outcome that you see. And that's exactly the reason why people call random variable, right? The quantity or the value of x is well defined. If you give the particular realization, you know what exactly the number is going to be. But what you don't know a priori is what omega is going to realize, right? When you just roll this. Before you roll, you don't know which one of these omegas you will come across, right? So this omega is just one element of this. And just for this reason, this well-defined function, right, is just called a random variable, right? So in this case, for example, if you just put, right, real numbers here, well, numbers or the okay, these realizations range from 1, 1 to 6, 6. So the smallest possible sum is going to be 2. Then 3, 4, 5, 6. It goes like this. And the largest is going to be 12, right? And x then, if it is just a mapping, it is like going to be what? So if omega turns out to be this, right, it is going to be mapped to 2, right? X is going to map these two things. If it is 1, 2, it is going to be mapped to 3, right? And if it's 2, 1, it is the same, right, for this be specifically. Actually, we could actually just write for sure that they are going to be mapped here. And if you just pay attention, so you will see that all these diagonals will together be mapped to one distinct integer like this. So all these arrows together will be just enough to define this. Okay? X is just a function, right? Nothing else. And as I said, it is a random function because which one of these pairs will appear is unknown a priori before we roll the die. Therefore, we just call it a random variable, or random function, actually. Random variable. Okay? Okay. Now, instead of events, we use random variables because they are more appropriate for some, or more convenient to use to model some of the problems. All right? But each event actually induces a very natural random variable. A very natural random variable. And what is that? That is actually also very elementary. An elementary event, a random variable, but also fundamental. I mean, at this level of class, I cannot explain how you can use these elementary random variables to basically do almost all the work in probability. But I can illustrate, and let me do that. Right? Let me do that. And okay. Okay. So we saw one example of a random variable, right? So the other example. Let's say A is just any event, and when I will use this awkward notation, 1 subscript A, alright? So this is probably, is this the first time you see if number is used to denote a function? You are used to use f of x to denote a function, right? But this is also a function. And if it is a function, right, and if it is a random variable, it is supposed to map each realization in sample space to a number, right? So it is fair to write like this. Treat this entire stuff like f. It's just a symbol for us. Don't allow it to confuse your minds. Right? I do it like this because this is associated with event A in the following way. It takes value 1. That's the reason why people use 1. If omega belongs to event A and 0 otherwise. Okay? We should not allow this to become a barrier between what the message it is trying to convey, alright? And what it looks like is here. So the name for this thing is, well, people call it the indicator random variable. Of event A. Why do they call it like that? It indicates whether the event A has happened or not. Right? So you, for example, in this thing, right? So that was a random variable. I can define first an event, simply just a subset of this omega, and then introduce this indicator random variable. Let's call A as the event that, okay, okay, what can I say? Okay, the number on the face of the first die, right, equals, well, or is even. Let me do that like is even. It is 2, 4, or 6, right? I just define an event, right? So, right, we say, right, that event A has happened, right? When do you say so? If, right, after you roll the dice, right, the outcome, right, falls into set A. Set A, right? That's what we when we say that when A has happened. What exactly is this? This is just a qualitative statement, right? You can just put all the possible pairs which is consistent with this definition. What are they? They are like, okay, it could be 2 something, right? 4 something, or 6 something, right? There are too many of them, but we can just write it like this, right? The 4, 1, okay, this is 1, this is 2, and 4, 6, and this is 6, 1, and this is 6, 6. Right? Do you agree with that? Huh? Does it make sense? Huh? Okay. So, for example, you roll the die, you observe 2 and 3. Right? Since you know that this belongs to A, your conclusion is what? A has happened. Event A has happened. Right? On the other hand, if you observe 3, 2, right? Well, this doesn't belong to A. So in this case, you say that A has not happened. So this is elementary, but I know if you have not thought about it, if thoroughly about it, then sometimes it is confusing. Now, in this case, well, either you say so, or you can just say, okay, well, this is my omega, right? Because that's what I have just observed. That's the realization. Right? Now, what happened to this one? It is 1. Because you check the definition. If omega belongs to A, then the value of the function is by definition 1. Of course, this is true. In this case, the realization turned out to be this pair. I should probably put actually like this, right? Because this is omega itself. Who cares? Sometimes I just omit them, right? In this case, it is 0. Right? Okay. So the first thing, this one is just part of the notation. You don't pay attention to that. You look at this thing as a function. You put a number or a realization here, and then check this row. Does it belong to A? Then the value is 1. If it doesn't, value equals 0. Right? Okay. It indicates whether the event A has happened or not. Just the way we exemplify it here. Right? Why are they so important? Huh? Why are they? Okay. I haven't introduced the expectation. That's too bad. Okay. First, we introduce that before I illustrate why they are important. For any random variable x, right? An indicator random variable is just an example. You can define the so-called cumulative distribution function, right? As well as expectations. So we have to remember them. Right? So since x, right, a random variable, is real valued, you can compare this thing against any number given to you, small x, right? So this is an event, right? It is event because this is the shorthand notation, right? So why don't I just write it quickly like that? So this is shorthand notation for what? Collection of all omegas such that when you plug this omega into this function, the value is less than or equal to x. You collect all these favorable things. Well, first of all, it is just a subset of omega, right? Therefore, it is an event. Therefore, you have every right to talk about its probability. What is the likelihood that the random variable is less than or equal to 4.6? You can do that, right? Since we are lazy, we don't usually write like this, we just write like this, but you always remember that this means that, right? And this has a name. It is, I guess your textbook uses this notation. Capital F, for no reason, is used to denote it, and it is known as cumulative distribution function. Alright, distribution function. Even this is too long for us to write, so we usually just use the short and CDF for that. Alright? Okay. In this course, we will usually see what we call a discrete random variable. A discrete random variable, right? If, right, x can take at most countably many different distinct values with positive probability. If x, okay, can take at most countably many distinct values. Right? And in that case, right? Maybe I should give a name for this one. That's gonna be helpful here. Count the many distinct values. Okay, let me continue like x1, x2, and so on. So I just have to give names to those counting many. Counting many means that you can count. Things that you can count. Okay, you can put one on one corresponds between non-negative integers. Things that you cannot count is like the real numbers. Take interval from 0, 1. There are more than just what you can count. Anyway, just get this picture, and the rest is not so much important. Okay, and here for every xk, right? Sk changes. So you can ask what this probability is, and you can even give a name. Let me call it by a sub k, right? For each k, right? So these are all going to be positive if they are the ones, the non-trivial values. All right, and you can check. Then that we have, right? First of all, AKs are numbers between 0 and 1. If they are distinct, actually I don't even care, so this must be the case. And when you sum them up, right, over k, it should give 1. Right? So any sequence of numbers between 0 and 1, AKs, which also satisfy this, they all sum up to 1, for any such sequence, you can find a random variable for which that sequence is gonna serve as the so-called probability mass function, right? For a random variable x, if you calculate numbers ak, right, we know that they should satisfy these conditions, and it has, the sequence has a special name. It is called the probability mass function. The short notation or the shorthand acronym for this is PMF, right? And it has this property. And as I said, the reverse is also correct. For any sequence of numbers AKs, between 0 and 1 satisfying this constraint, you can in fact define a random variable for which the sequence is going to be a probability mass function. Maybe I should say of random variable x. So that's the story for discrete random variables. Right? And then we also have, that's correct, so-called continuous random variables. Right? And what is that? So a random variable x is called, or that's not a good way to write it, let me see, is said to be continuously distributed with probability density function f, right? If, right, whenever you need to calculate the probability that, okay, I shouldn't, I guess, probability that x is between two real numbers given to you, a and b, you get this number by simply integrating density function between these two numbers, a and b, right? For every a and b. Right? Okay. And by making A and B arbitrarily close to each other, you can show that f is not an arbitrary function. It is, first of all, a real-valued function, right? Okay. Fx is a non-negative real-valued such that if you let A go to minus infinity and B go to plus infinity, right? This simply gives you the probability that x is between plus and minus infinity. Since x is a real value and these are not real values, so this is actually the range in which x can live anyway, and this must happen with probability 1. So what we learn from the definition, that f is such a function that it is first of all non-negative, and when you integrate it over the entire real line, it gives 1, right? So any function with these properties deserves the name probability density function, and there is a way to construct a random variable, a concrete example for which f is indeed the following relationship. Right? That's only a mathematical fact. So we are usually not going to go in that direction. We will usually define a random variable in a very natural way. The application will just hint us what random variable we will be working, and somehow we will figure out the density functions. Whenever we need to calculate some probabilities, we will just use integration. And integration should not scare anybody in this classroom, right? It's not a calculus class. I'm not going to emphasize anything about the complex things. But over time, you may want to just review your calculus if you want to be honest. Okay. All right. Let me take a couple of more minutes and let's see. Maybe we can also. So this part is a little boring. I'm just giving all the definitions, right? So, but we have to do that. So you should remember them, and then we will start using them in examples, right? And the relationship now, I have distribution function. Let's say x is a continuously distributed random variable, right? And we have the density function here, and the distribution function. By definition, what is this? This is the probability that x is less than or equal to small x. Lower bound is not there, but it is, of course, by that we mean that it extends to minus infinity. So this is like the integral of the density function between minus infinity and x. In all the applications, in the examples, we will consider f is going to have nice properties that will allow us to take the derivative of this, or just, I should say that f is going to be just the integral of its derivative, right? So you can take the derivative to find the density function. So if you are given the density function, you can calculate the distribution function by integration. But if you are given the distribution function, you can take the derivative to find the density function. Right, like this. And I might also write things like this. I usually don't use f explicitly. If we ever need to integrate something with respect to density function, you can go back to this one. Okay. You can check that the probability that x is between x and x plus a small increment, positive increment, right? This can be approximated by fx times, right, the value of this function at x times this increment. And the reason is, well, you will, I hope, remember what integration means, right? So this is x-axis, right? The f is that's the function sitting inside the integration. It's just a function. And if you want to integrate it between, right, here what does it say? Between x and x plus dx. Okay, let's first write the original definition. This, if you just use the original, right, definition, you replace a with x, b with x plus dx, right? So you look at this, and you integrate f, right? So we look at this. So x is here, right? Well, x plus delta x is here. Well, I exaggerated too much. Actually, if dx is too small, this number is going to be somewhere here, right? X plus dx, right? So if dx is small, right? Go it like that. So what is the area under the curve? If the width is too small, it is almost the same as, well, this now looks like just a rectangle, and to calculate the area of a rectangle, what you do is you just look at the height, and then you multiply with the width, right? There is a small curve here, but as I said, we are free to choose dx as small as we want, so that this approximation of the area under the curve with the area of the rectangle becomes precise, right? And then you can just write, instead of this, as height, which is an x, the height is going to be just the value of the function f times the width of this rectangle, which is the x plus dx minus x, which is just dx, right? So we have that's why do I care about this? We couldn't just get rid of this letter f from our side, and we will never have to again remember what f was associated with. When you have too many random variables around, then you have to introduce too many distribution functions. Then we will not we won't need to do that in the future. All right, and finally, we can define the expectation. Expectation of a random variable. Right? We denote it by E applied to X, right? So you may have noticed my letters, the letters that I use. P with this is actually bold, it is called boldface. P, when you don't have a computer, that's how you can actually print a boldface letter. It's similarly like this. So if I use P or E, just remember that they don't mean the expectation of probability for my in my notation. They must have probably standing for some other stuff. Anyway, this is going to be, so we can define this, right, as the weighted average of the values a discrete random variable can take, right? So if it is xi, for example, and if the random variable x takes this value with probability x equals xi, I take the weighted average, right, of values the random variable x can take with the probabilities with which that random variable will take, right, that day. So that's by definition, right, the expectation. So we can just actually put here 2 dots, right? So if x is discrete, unfortunately we have to make this thing, we have to distinguish the definition at this level of class at least, right? But if x is continuously distributed, right, then it is again a summation, in fact. But since there are more than countable many different values the random variable can take, that summation in the limit becomes an integral sign, right? If you remember from your calculus course, your professor might have actually told the story behind this symbol, right? It is nothing but just S, standing for sum. So actually these two formulas, what is it, by the way? So it is fx times fx times dx. These two formulas are not different at all from each other. Okay? Here we said what? Expectation for a discrete random variable is weighted sum of the values the random variables can take with the probabilities. Here we have the same thing. It is the way that some of the values the random variable can take with the probabilities. Now see, that's the probability. That random variable x can take x almost near x. Because the x is so small that you cannot actually distinguish x from any other value in this small interval. So, and the way to cure this illness, I call it illness because you have to just deal every expression of the theorem that you write on the board for discrete and continuous time separately. We don't have to do that. We can just write, for example, for expectation. This is, okay, borrow integration from there. X times the probability that x takes values near x. So capital X, the random variable, takes values near small x. This is just a notation which stands for probability x equals small x if x is discrete. And, well, okay, now I have f of x times dx if x is continuously distributed, and I don't have space here, continuously distributed with probability density function f. You take one of them, plug here, you get either this or that. Right? But the idea is the same. It is just weighted average of the values of random variable, where weights are the probabilities with which those different values are being taken, right, by this thing. And one small, okay, two things perhaps, right? And they are related with the properties of expectation. Let's also list them so that we have, we don't have to worry about this stuff. First of all, whenever you need to take expectation of maybe, okay, before that I could just mention the other one because you can use the other to derive this. So if you are given a function g, a real valued function, so g is a function from R to R, right? So you can, okay, too fast perhaps, okay, sorry about that. For every function g from R to R, right? Okay, if you just denote by y the composition of x with random variable x is itself a random variable. What do I mean by this? Just the way x is a mapping from omega, right, sample space to real line, y is itself also a mapping from omega to real line, right? So it's omega here, right? And then there is real lines here, real line here. So you know that x maps omega to this one, and what you then have another copy of g, and g another copy of real line, and the g maps r into r, right? Again. So when you just compose g with x, that's what exactly we mean by this, right? And then this thing, right, like this, it is y, right? Right? Right. We should just, this notation is a lot more convenient here because we can put omega here, right? So this is itself a mapping from omega to r, therefore it is itself a random variable. So then you have every right to talk about distribution function, cumulative distribution function, density function, and expectation of this random variable, and you can use the usual formula to calculate expectation, but there is a shorthand way to write calculate the expectation for a function of the same random variable g. So this is now weighted average of function g composed with the values that random variable x can take times density function of the same random variable x dx. Alright? So we will use this a lot. And finally, let me just, if you take g of little x, right, a function, a affine function, right, affine function, and use this one, you can actually show right away that this is the same as a plus b times the expected value of x. Namely, expectation. Right? So this is like, we call it an operator. It operates on whatever's is standing on its right. It is linear. Right? It skips the constant. It goes out. Doesn't care about the constant that you add. It doesn't care about the constant you multiply with either. It just moves ahead like this. Right? I said actually I would like to illustrate the use of indicator random variables, but unfortunately we have to wait, I guess, next class. I'll show you a lot of examples where we will see that the indicator random variables are lifesavers in a lot of problems. Okay? Okay, that's enough for today, I guess. Okay, I'll see you on Thursday. Yeah?